Example 5. A student prepared a 0.1 molar solution of propanoic acid and found that the pH was 2.96. What is the acid dissociation constant for propanoic acid? Well, the first question you need to ask yourself is, what is the acid dissociation constant? If you do not know what the question is asking for, it'll be quite difficult to actually answer it. Acid dissociation constant is simply Ka. So this is another way for us to ask the value of Ka. So to begin, we have propanoic acid. CH3, CH2, COOH. This is not one of the 6 strong acids, so we need to react this with water. Use our equilibrium arrows to give us CH3, CH2, COO negative, and H3O positive. We were told that we had a 0.1 molar solution. However, we were not told that this was specifically at equilibrium. So we need to use our ice table. Water is not included in an acid dissociation constant, so we can leave that out. We initially had 0.1 molar propanoic acid, and we always have no products to start. We lose reactants, we gain products, all of which have the coefficient 1, and the equilibrium line are the first two put together. Once you have your ice table set up, you go back to the question for the extra piece of information. And in this question, we were told that the pH was 2.96. So you ask yourself, what can you find using pH? And using pH, you can find the hydronium ion concentration at equilibrium. It's 10 to the negative pH, so that would be 10 to the negative 2.96. Notice that the pH has 2 decimal places, so our answer should have 2 significant figures. And that would be 0.0011 molar. Again, this is the equilibrium concentration of the hydronium ion. So at this point, you have to ask yourself, what did you say was the equilibrium concentration of the hydronium ion in your ice table? And if you find hydronium and you look for the equilibrium line, you'll notice that you called that X. And therefore, we have solved for X. Once you know the value of X, you can then find the other concentrations at equilibrium. CH3, CH2, COO negative at equilibrium is X. So we know this to be 0.0011 molar. Propanoic acid at equilibrium we said was 0.10 minus X, which still remains 0.10 molar. Once you have all of your equilibrium concentrations, you can then set up your Ka expression. Remember that it's products over reactants raised to the power of the coefficient. Once you have your equilibrium expression set up, you can fill in the equilibrium concentrations. One of the moles per liter, we'll cancel it with the moles per liter in the denominator. Our answer for Ka should have 2 significant figures, and that would be 1.2 times 10 to the negative 5 moles per liter. Our final example in this section, the pH of 0.250 molar HF is 2.036. What is the value of Ka for hydrofluoric acid? Well, hydrofluoric acid is not one of the 6 strong acids, so again we need to react this with water. Since it's not one of the 6 strong acids, we will use our equilibrium arrow. And this leaves us with the fluoride ion and the hydronium ion. We were told that the concentration of hydrofluoric acid was 0.250 molar. However, it does not say that this is at equilibrium. So we need to set up our ice table. Water will not be included in the Ka expression, so we will not include it in our ice table either. The initial concentration of HF is 0.250. We always start off with no products. We lose reactants, we gain products, and the equilibrium line is the first two put together. Once you have your ice table set up, we go back to the question for the extra piece of information, and that would be that the pH is 2.036. Just like in example number 5, from the pH you can find the hydronium ion concentration at equilibrium using 10 to the negative pH. That would be 10 to the negative 2.036. Since our pH has 3 decimal places, our concentration will have 3 significant figures. So this is 0.00920 molar. Again, this is the equilibrium concentration of the hydronium ion. According to you and your ice table, the equilibrium concentration of the hydronium ion was X. So we have now discovered the value of X. Once you have discovered the value of X, you can then discover the equilibrium concentrations of the other species present. The fluoride ion is also X, so this will also be 0.00920 molar. And hydrofluoric acid at equilibrium is 0.250 minus X, which is 0.241 molar. Once you have all of the equilibrium concentrations, you can then set up your Ka expression. That would be products over reactants raised to the power of their coefficient, and in here all coefficients are 1. Once you have the Ka expression set up, you can then plug in the equilibrium concentrations, including units. One of the moles per liter in the numerator will cancel out the moles per liter in the denominator. Our answer should have 3 significant figures. So here Ka is 3.51 times 10 to the negative 4 molar.